So, singular value decomposition. So, last time we talked about like eigenvalues and diagonalization, I think, right? Past couple times we've talked about stuff like that. So this time we're talking about singular values and singular value decomposition, which is kind of related. So there's whoa, is that you? I don't know. Strange sound. Anyways, so I'm going to do a quick proof. So theorem, the eigenvectors for a symmetric linear transformation are pairwise orthogonal. So that means if you took the set of all eigenvectors, each of them is orthogonal to every other one, right? They're sort of pairwise orthogonal. So how do we prove this? This is unrelated to singular values. It's just a sort of standard eigenvalue proof, or eigenvector, I guess. Symmetric, right, means that that if you have a transformation T that's symmetric, say you think about it as like a matrix, the transpose of that thing is equal to the matrix itself. Right, so if you take the transpose of it, it's the same. So let's do it using matrices because sometimes matrices are easier to think about. We'll start the proof. So say that we have A, which is a real matrix, n by n, I guess we'll say, over the real numbers. So it's a n by n matrix with real entries. And let's say that we have vectors x and y. Then we have, I think this was from one of your lectures, we have a theorem that says that ax with y, inner product of ax with y, is equal to the inner product of x with A transpose y. So you can move the A over, but you take its transpose. Good with that? So, but if A is symmetric, then we get that A transpose equals A, right? So this sort of simplifies a bit. Let's say that, so let's say A is symmetric, and let's say that x and y are two eigenvectors, any two, right? And maybe let's say that they have corresponding eigenvalues of lambda 1 and lambda 2. Good with that? So what that means, I mean, I guess, is that lambda 1 x is equal to ax and lambda 2 y is equal to ay. Great. Okay, so if we take a look at this lambda 1 with x and y, we can bring that lambda 1 in, right, by the linearity property. Lambda 1 x with y. But now we have lambda 1 x, which is the same thing as ax, right? So we can bring that, or change that into an ax and we get this. Any idea what we can do now? It's on the board, it's just. Yep, exactly. So it's equal to x a y. Now really it's A transpose, but A transpose is equal to A, right? I'm just simplifying it. But now we have AY. AY is the same thing as lambda 2 times y. Lambda 2, oh sorry, I should work this up. X with lambda 2y, right? Now since A is a real matrix, that means its eigenvalues are real, right? So, I mean, you could think about like the conjugate, taking the conjugates of this, but it's real, right? So we can just pull out that lambda 2, xy. So what we've shown is that lambda 1 xy equals lambda 2 times xy. So that means that lambda 1 xy minus lambda 2 xy equals 0, right? If they're the same thing, you subtract them, they should equal 0. So what that means is that lambda 1 minus lambda 2 times the inner product of x and y equals 0. If I factor out x, inner product of x with y. Now here's the thing. If x and y are distinct eigenvectors, so they're different, then that means they're going to have different eigenvalues, right? So we have two distinct eigenvalues. That means this difference here is not 0, right? So because x1 is not equal to x2, or not x1, lambda 1 is not equal to lambda 2, that thing can't be 0. So in order for this product to equal 0, that means this thing has to be 0, right? The inner product of x and y is 0, and that means that x is orthogonal to y, right? And since we picked that for any arbitrary eigenvectors, right? We just said pick any two, then they're all pairwise orthogonal. Good with that? Cool.
For the step that you take nominal out, so xy must be real space.
Mm-hmm. So there is like a conjugate piece, right? So really this is lambda conjugate, lambda 2 conjugate. But since A is a n by n matrix with real value entries, since it's real value entries, all of its eigenvalues are going to be real. So the conjugate of a real number is just the same as the number, right? Does that make sense? Cool. Any other questions? And the reason you know it's a real value, or like a real matrix, maybe I should have said that a bit more explicitly, is because I use the term symmetric. Symmetric only applies to real valued matrices. If it was a complex valued matrix, then you would see Hermitian as the term. So symmetric only works with real. Hermitian means, like, broadly speaking, that A is equal to A transpose conjugate. And we usually denote that as like A star or A Hermitian. Does that make sense? Sometimes there's a few notations for it. Some people will write AH to mean like Hermitian, and physicists will write A with like a little dagger. Yeah. So if you see any of those, that's all that means. It's just symmetric, but the conjugate is symmetric. Okay, any questions about this proof? Make sense? Yeah.
How do you know that lambda 1 and lambda 2 are distinct eigenvalues?
Because, I mean, maybe I didn't write this, but here I'm saying that these are distinct. They're distinct eigenvectors.
Okay.
It's just the assumption. Any other questions? Good with that proof? Okay. So, what does that have to do with singular values? We just needed to get through it so that we could talk about singular values. So we say a transformation T is orthogonal if x, the inner product of x with y is equal to the inner product of the transformation of x with the transformation of y. So what that means is that the transformation doesn't change inner products, right? We say that T is orthogonal, or the matrix is orthogonal. You might have seen this in like linear algebra, like the first linear algebra, which would have been that A inverse is equal to A transpose. These two properties are the same thing. That you can go through and prove that those two are identical, but it's a good exercise. Where A is just like the matrix representation of T. So those two things mean, if either of those are true, it means that a matrix is orthogonal. Okay. One thing that is kind of interesting is that an orthogonal transformation is always a rotation. So why does it have to always be a rotation? Because you can't change that inner product, right? So if you're taking two vectors and you rotate them by the same amount, you're not changing the inner product, right? But if you were to like stretch it or something, or like flip them or something, now you're changing the inner product, right? So the only transformation that these could be is something that rotates, right? Like a rotation. So orthogonal matrices are rotations. And another fact that maybe you didn't know is that diagonal matrices are the same thing as scalings. So like taking it, stretching or shrinking or flipping, right? And that should make sense, right? Because you're just multiplying each entry by the whatever's along the diagonal, right? Cool. Okay, so now, what are some of the problems with diagonalization? There's sort of two key problems. Does anyone have any ideas as to what they could be? Like restrictions that diagonalization has?
The eigenvalues need to be distinct.
The eigenvectors, not the eigenvalues, the eigenvectors need to be linearly independent, right? So yeah, the eigenvectors need to be linearly independent, that's true. There's one more that's like maybe a little too obvious. You're all like going way too far, I think, yeah.
It needs to be square.
Yeah, A needs to be square, right? What if your matrix isn't square? You can't find the eigenvalues, so there's no diagonalization, right? So the question is there a thing that we can do for a non-square matrix that is similar, right? That's similar to diagonalization. And the answer is yes, singular value decomposition. You can decompose any matrix A into three matrices, U, sigma, V transpose. I know that looks scary, but it really shouldn't. It's just three matrices. Where U, the columns of U, so columns of U are the eigenvectors of, and I don't want to get this wrong, so I'm just going to look back. The eigenvectors of A transpose A. Now A transpose A is always going to be a square matrix, and it's always going to be a symmetric matrix. You can maybe show that by testing it out a little bit, right? If you take any matrix and do the transpose of it, multiply it by itself, it's going to be square and symmetric, which is where this theorem kicks in. That's why I showed you that. The second one is that the columns of V are going to be the eigenvectors of A transpose. Now notice I wrote the columns of V, but we're putting V transpose here, right? So you have to figure out what V is and then take its transpose. So in practice, what that means is that the rows of V transpose are the eigenvectors of A transpose. Got it? Then the last one is that so maybe I should write this. So sigma is a diagonal matrix with diagonal entries sigma. Now maybe you're wondering what that small sigma is, rightly so. So if lambda 1 through lambda n are the eigenvalues of A transpose A, then sigma I is equal to, we just defined it to be equal to the square root of the ith eigenvalue. That sigma is called a singular value of A. So to find the singular values, you find the eigenvalues of A transpose A, which are the same as the eigenvalues of A transpose. So it actually doesn't matter what order you do that. They have the same eigenvalues. So you find the eigenvalues of that A transpose A, and then you square root them, and that gives you your singular values for A. Does that make sense? So yeah, so those are called the singular values. If you put those along the diagonal, then that'll give you your sigma matrix. So you can decompose any matrix, doesn't matter what size it is, into U sigma V transpose. Does that make sense? Just like how in diagonalization we could decompose any matrix into, what was it, P inverse DP, I think. So this is just another way you can decompose matrices. Yeah. A couple other terminology, and I always mess these up, so I broke them down. The eigenvectors of A transpose A are called the right singular vectors. The right singular vectors. And the eigenvectors of A transpose are the left singular vectors. Does that make sense? Any questions about singular value decomp? Maybe I should answer why it's useful. This is incredibly useful in the real world. So singular values highlight what information in a matrix is important and what is not important. So like if you're doing calculations with computers, maybe you want it to be really precise on some values of that calculation, and maybe other ones don't matter quite as much. The example I saw online was, say you had a computer and you wanted it to sort M&Ms. You had like a picture of M&Ms and you wanted it to sort them. You know, maybe the computer could sort them based on like how perfect of a circle the M&M is, or it could sort them based on like if there's any distortion in the letter M on the front, or it could sort them based on like how much chocolate is inside, right? Or it could sort them based on color, right? One of those is pretty obvious, right? So if it's sorting it, you want it to place the most focus on the color, right? You don't really care about the rest of it. So that's what these singular values tell you, is that when you do a singular value decomposition, it shows you what values are important in a certain system. So they're useful in finance, right? Because like if you're doing some sort of financial analysis, it's important to know like what metrics are important in your business or whatever, or in like the stocks. It's important in image compression because it tells you what parts of the image are important to keep if you're trying to compress something. And it's important in principal component analysis, which is big in data science, right? If you're doing data science, that's PCA is a big tool that people use. Any questions? All right, I'm going to stop.
Bev, you said